Okay, now we're going to do an example 14a based on the equations that I distinguished in the last video. So let's read this question first. So a source of sound emitting at a frequency of 480 hertz is moving directly towards a stationary observer at 50 meters per second. If it is a hot day and the speed of sound is 350 meters per second, what frequency is received? Okay, so obviously first we're going to have the equation that has u sub s because it's the source that's moving, right? So we're going to write that down. I'll use black ink. F is equal F apostrophe. So in one of these, in the last video, I wrote it out as like F and then brackets V over V minus U or V plus U. So in this one, I'm just going to move the F up because it's going to make it like look a lot better. So it's going to make no difference. Just know that. We're going to have F of V over. Now this is where we have to see what's happening, right? So we have V. Now is it plus or is it minus? So the sound is moving towards us, okay? And we learned in the last video, if it's moving towards you, you're going to need to start subtracting, all right? Because you want this side to become bigger than this. I mean, sorry, you want this to be bigger than the actual, all right? You want F apostrophe thingy to be bigger than F. So now all you need to do is plug in. All right, so we have F apostrophe is equal to, let's see what we have. It's emitting a frequency of 480 hertz. So you have 480. So it's moving the source is moving directly. All right, let's find V first. So V is the wave speed. So the speed of sound is going to be 350. So we have to multiply this by 350. And the bottom is going to be 350 again. Subtract the speed of the source, which is 50 meters per second. And then all you're going to need to do is solve. Yeah, so you're just going to need to solve. So I'll do it now. 480, you don't even need to solve for this one, to be honest. 480 times 350 in brackets, all over 350 minus 50. Now this equates to 560. And because we're looking for the frequency which is received, this is going to be in hertz. All right, now I'm going to do B. So B is asking what frequency would be heard on a cold day when the speed of sound was 330. So we're using the same setup. The only thing we're changing is this number right here. So what we're going to write, I'm going to write this in red, is F is equal to 480 again, because this hasn't changed, times, now we're doing 3, not 50, remember, and question B, 330, all right? All of this is going to be over 330 minus 50. And then all you need to do is solve. All right, so 480 times 330 all over 330 minus 50. And you would get, it would be an uneven, by uneven I mean it would be a decimal. But we're going to round it. So the answer would be 5 in decimal form. With decimals, it would be 565.714. But if we want to round, we're going to have 566, and this is going to be in hertz yet again. Question C is not relevant to the our equations, but is good to know. Explain why the speed of sound is less on a colder day. So we learned this a while ago. So sound, the speed. So sound is a wave. The speed of a wave is only affected by the medium in which it travels through. And in a colder day, these molecules. So basically, what I'm trying to say is that on a hotter day, let's say the molecules will be able to move faster because there's less resistance. On a colder day, things are kind of more clumped together, and then that would mean that the molecules will start moving a bit slower and will lower its average speed. I think we learned this in a previous lesson. I'm not sure which one it was. Let me check actually. Which lesson was this? Because I vividly remember this. You might be hearing my pages move because I'm looking through my notebook right now. Because I just want to make sure that I'm doing this all on facts. All right, here. How can you change the speed of waves? So sound. Sound is increased by temperature. Okay, sorry, that's my bad, not medium. So the temperature of sound, the higher the temperature, the faster the speed. The lower the temperature, the lower the speed. And that's because of the sound equation, which is 332 meters per second plus 0.6 when then times the temperature in Celsius. So if it's a colder day, the speed of sound is going to be a bit slower, not by much, but just a bit. And if it's a hotter day with an increased temperature, the speed of sound is going to increase. And yeah, that's it.